Programming World 4 so that these clouds would work was pretty interesting. Every frame, a video game must know how long it should simulate the motion of its objects in order to make the rendered scene look smooth. For most games, the simulated time matches the real time measured by the clock on your wall. If the game is displaying at 60 frames per second, then each frame should represent 1/60th of a second of simulation time. Braid plays around with time very heavily though, especially on this world. Through World 4, we use the player's speed at the start of the frame to determine how much time should be simulated. But as explained in another note on this level, when you're riding on a moving object, this relationship gets very complicated. It appears to have an infinite regress, where your motion causes the platform you're riding on to move, which causes you to move even more, which makes time go forward more, which makes the platform move further, and so on forever. An unsophisticated implementation might run many simulation steps instead of one, simulating ever smaller amounts of time until we decide that the residual amount is so small that we can ignore it. The problem is that running a simulation may require the computer to do a lot of computational work, which takes time. Running many simulation steps takes a lot more time than one step, and in this game, the amount of work to do in each step does not really decrease as we make the simulation time shorter. So we would be in danger of taking too long to compute all the simulation steps, resulting in a low frame rate for the game, which would feel pretty bad. Fortunately, we don't have to do a bunch of simulation steps if we know a little bit of math. The result of walking on a moving platform can be represented as the summation of a geometric series, and provided the speeds of the objects you're riding on are reasonable, the series converges. It's representable in closed form very simply. We just need to do an extra add, a multiply, and a divide. Much cheaper than running many simulation steps. We'll cover the exact math for this in the next part. I wanted World 4 to have a feel that matches the rest of the game in basic situations. You run around and jump and climb at the same speed as in other worlds. Then we use your motion to drive the advancement of time for everything else in the level. So first, we run our simulation step for only the player, holding the rest of the world constant. This gives us a value, delta x0, the amount by which the player moves in the x direction if the rest of the world were totally still. Most of the time, it's very simple from there. If we want to know how much time should pass for the rest of the world, we just take delta x0 and multiply it by some factor f that we use to determine how much time passes for each unit moved in space. This constant is arbitrary. We can turn it up or down, and time will move faster or slower relative to your own motion. We'll call the amount of time that passes as a result of this conversion delta t0. Delta t0 is just delta x0 times f. Now we're concerned with a special case. What if the player is standing on something that's moving? As we mentioned, the movement of whatever he's standing on should carry him as time passes, affecting the total x distance that he moves. So the amount of time that passes with each step should be different. Once we have computed delta t0, we know how far the platform or cloud would have moved in that time. If v is the velocity of the cloud, it will move by v times delta t0. Because that cloud is carrying the player, this also represents the additional distance the player will move. So if we say that delta x1 equals v times delta t0, the total distance the player will now move is delta x0 plus delta x1. But this extra distance moved by the player means that more time should pass. If we say that delta t1 is this additional time, so that the total time passing so far is delta t0 plus delta t1, then just like before, we use f to convert space to time. Delta t1 is equal to delta x1 times f. But so far we've only simulated the platform for a delta t0 amount of time, so we need to add extra time, which means adding extra distance, which means adding even more time. So we can compute delta x2, delta t2, delta x3, delta t3, and so on. Each delta x is just v times the previous delta t, and each delta t is just f times the previous delta x. In the game, because of the way we're plugging this into later World 4 code, we solve for the sum of all delta x from delta x0 to delta x infinity. If you wanted to think mainly about time instead, you could solve for the sum of all the delta t's. Because we just multiply v times f every step, this is a simple geometric series. It converges as long as v times f is less than 1. If the platform were moving fast enough, it could carry the player faster and faster with each step, so that an infinite amount of distance is traversed, which would make it pretty hard to play the game. Fortunately, as long as v times f is less than 1, there's a closed-form solution for this equation, and this is it. To get the sum total of an infinite number of time steps, we just divide delta x0 by 1 minus v times f. Once I had decided on the basic way this world works, that the player would go forward in time, while all the gameplay objects would go backward in time of their own accord, there remained a big question about how to make this actually happen in the code. Since the gameplay engine of Braid is all about recording the history of objects and playing them back later on, the most obvious idea is to use that same code just to make everything go backwards. During development time, you would set up a level with monsters and whatever else, and you just let it play with time going forward and record the history of that, just like we do for normal rewinding. Then, when someone is actually playing the game, you load that recorded history and play it backward, and the player is just exempted from that rewind and simulates forward normally. This was the first thing I thought of, and immediately I felt it just wouldn't be very good, because you'd never be able to affect any of the objects because those objects could only do what was pre-recorded. If you couldn't affect anything, it seems the game design would become monotonous, and all the levels would just be about bouncing off invulnerable monsters, or whatever. I wanted at least some reverse causality. For example, jump on a dead monster to make it alive. This brings a little bit of magic into the dynamics of that world and allows there to be cause and effect for something besides the player. Now, there might be ways to do this by pre-recording everything. For example, you could record multiple histories and branch between them based on the player's actions. This would use a much larger amount of memory. It would be very messy and hard to program, and it would constrain possible player actions only to the places that were pre-computed during development time. This constraint might prevent you from designing what you really want to design. The much more appealing alternative was to make a way for monsters and gameplay objects to somehow simulate themselves backward from moment to moment in the same way that they go forward. Monsters would undie and unfall. Figuring out when monsters should undie is not too hard. Clearly, it's when the player is bouncing off them. But when should they unfall, and how does the game know when and where they started falling so they can simulate back to that point? There are a few different ways to do all this. The solution I implemented does involve simulating the level forward at development time, like the pre-recording idea would have. But instead of recording the history of all the objects, I added some special code that creates invisible markers wherever major events happen. For example, when a monster hits a surface and bounces off, we create a marker and also record the velocity at which the monster had been traveling when it hit the floor. We save those markers with the rest of the level, and now when the monsters are walking backwards, there are indicators of where they should unbounce from their fall and then unfall upward. And at some point up in space near the ledge is a marker that says, if a falling monster passes through this space, it should land here. The idea is that during gameplay, we just simulate monsters backwards. So if a monster's alive, he walks backward, and if he hits a marker, we make something special happen. Here are the bounce markers on this level. Each marker says, hey monster, if you get here, launch yourself upward with some particular velocity, the negative velocity of the one we recorded when playing time forward. As long as the monster did not fall far enough to reach terminal velocity, then this should launch the monster back up to exactly the place where it fell off the platform. In reality, because of small inaccuracies in the way the game is simulated, these markers did not reproduce the motion perfectly backward, and I had to tweak the results by hand at least a little bit. There's another kind of marker up here on the cannon that says if a monster ends up inside this cannon, make it disappear. Also make the cannon fuse start unburning. We also need to start playing the sound effect for the cannon shot from the end and going backwards so that it finishes just when the cannon would fire. This is accomplished with more markers. When playing the level forward in developer mode, when sound effects finish playing, we put markers wherever the current monster is, so that during gameplay, when time is going backwards, we know when to start the sound effect. In other words, the cannons are not firing based on time, but based on the monster's position. This jump to revive situation becomes a little weird, because what happens when you aren't jumping, but you're just standing there, and the monster comes up to meet your feet? If we're keeping with a strict interpretation of the rules of the game, maybe what should happen is that the monster just stays dead and keeps falling upward past you, because you couldn't have killed the monster if you weren't jumping. So, to unkill a monster, if we're being strict, you would have to jump into the air right above the dead monster's head at just the right time, such that it would be plausible you had bounced off it. But if the game were this picky, This might make levels extremely hard, and it might be really annoying to play. Hitting the monsters, unfalling quickly up the screen, would require difficult timing because the monster is moving very quickly and you can't see it coming because you need to hit it near the bottom of the screen where you're standing. And if the player isn't even sure that this is the right way to solve the puzzle, the difficulty in execution adds ambiguity. Is this the wrong answer, or am I just failing to do it properly? Is not something you want players to be confused about in a puzzle game. So, I made the judgment call that just standing on a dead monster would revive it, but pop you into the air in a jump. So in reverse, it looks somewhat like jumping on a monster to kill it. It's just that the positioning is slightly awkward. If I were designing the game again with the experience I have now, I might try harder to remove this standing bounce and make it workable that we require the player to jump. For example, I might redesign the level so that you can see further down below the playable area to see the dead monster coming up, which itself would be suggestive that you should jump on it. And I'd try to somehow hint the jump in other ways. But doing a good job would require changes elsewhere in the game. For example, if we let you see very far below the play area so that you could time the jump, it would feel very out of place compared to the rest of the game, where the floor is always near the bottom of the screen. There is at least one level where portions of the play area are pretty high up the screen, the pit, but that's because we want to make room for the pit itself. Not much play happens on the higher part of the level, which is off to the sides. And the rest of the game still sets the expectation that the ground is low down. One way to make this more natural would be to make another level earlier in the game that also has a high floor, and then have this level be a reprise of that one. Reprises are something we do a lot in the game already, but it's not easy to add more levels into a game that has a fixed number of puzzle pieces per world. Which other puzzle piece do I remove to make room for this one? And how do we make that level interesting? In order for it to feel good, the puzzle would have to have something to do with the ground being high up. But the gameplay excuse for this can't be reverse time because that doesn't happen until later in the game. So what could it be? It's just not easy to be a picky game designer. When confronted with the fact that reversal didn't work perfectly, so that monsters flung into the air by these markers did not reach exactly the place they came from when recording the markers, the ideal thing to do would have been to keep working on the simulation code until the reversal worked perfectly. But when you're overwhelmed by the number of things to do to finish a game, and the simulation code is already pretty complicated because it has to support all kinds of different rules from all the different worlds, it can seem much more appealing just to do the quick fix. And tactically, this is often the right solution in terms of actually finishing the game. Especially back when Braid was made, lots of independent games would fail because the authors just got overwhelmed by how much work there was to do, so the games never got finished. I was very, very mindful of this and wanted to finish the game at all costs. The downside of a quick fix is that the imperfect reversal could be a symptom of some much deeper problem that is affecting other parts of the game in a negative way. And by doing a quick fix, rather than investigating and fixing the deeper problem, we could be causing big bugs elsewhere. Maybe rare bugs that we would not catch in testing, but that would cause bad experiences for a significant number of players. Many other games have had exactly this kind of problem. On the other hand, the imperfect reproduction of the markers could be a simple issue that affects only the World 1 levels, like a simple dependency on the order in which we update velocity and position. I chose not to open that potential rat's nest and just do the easy hand tweaking and work towards shipping the game. And maybe this was the right choice because the game did get finished.
Is your, just quick technical procedural thing, is your method that the programmer art and the final art produced by the artist is a drop-in replacement, literally?
Oh, no, not at all.
Oh, so it's, you had to reprogram.
I had to do a lot of extra programming. And so the game was totally working, for example, without any kind of parallax scrolling in the background. It was one-to-one.
Right.
And just going from that to the parallax version with all these particle systems and stuff was a bunch of extra programming.
Yeah.
And we sort of did that over time as David did the art.
Yeah, that part I understand, but I mean, you didn't produce placeholder art for the parallax scrolling, right? So there couldn't be a drop-in.
Well, even so with these chandeliers, for example, we were working out the system by which we represent all these graphics in the game. And what I did was, David has like a Photoshop file. He's drawing the things in Photoshop. The way Photoshop works is there's a bunch of layers, right? And you can enable and disable visibility on them and all
I've been
these
using
things.
it since 1990.
Yep. And so we had this exporter. So rather than exporting bitmaps to some other format, right, we have an exporter that looks at the Photoshop file, looks at the layers, right, finds the sort of the bounding box of what pixels are set in that layer, possibly chops it into smaller pieces, both because there was a maximum texture size in those days, right, which is variable based on platform, but we could be like, well, we don't want any pieces to be bigger than 256 pixels wide or something. There are two things you want to do that are related in 3D rendering, especially back then, right? Even though this game is 2D, it was running on 3D rendering hardware, as it is still. One of the things that's very slow when you're using this kind of hardware is changing what bitmap you're drawing all the time, because I'm just going to say stuff that won't make sense to people who aren't programmers, but there's a very deep pipeline where the GPU is doing a bunch of things in parallel. And especially back then, much less so now, if you want to do something drastic like change what texture we're reading from, you basically have to like flush the pipeline, wait for all the current computations to finish, and then, and it's also just slow for your program to talk to the GPU and stuff. And so if you're going to draw, let's say, 1,000 rectangles on the screen. I don't actually know how many we do per frame in old Braid. Let's just say 1,000 as a number, right? That takes a lot of time. If you have to switch textures every single time, that's a lot slower than if you can draw, 50 rectangles all with the first texture and then another 50 with the second texture and so forth. Now, one thing that you often do in 3D, especially when you're drawing opaque objects, is you sort by texture. And again, this is a little bit of an older thing that people do less now, but you would sort by texture, you batch all these things together, you send them all to the GPU, and then you do the next ones. Now in 2D, it's actually not even that easy because we need to draw from back to front, because we have in this game all this translucency everywhere. Even things that are mainly opaque have, because it's drawn with a paintbrush that has a little bit of translucency at the edges. But also the look of Braid is that there's like a lot of sky pieces and a lot of particles and all these things that just blend together. And so you can't draw things out of order. There's two things that we needed to do. We needed to draw back to front, first of all, but then also as many things as we can draw at one time that have the same texture. We draw those in batches. So for a given level, that means that as many, like if there's a bunch of art that we think is going to be present in one level, we want to pack those into the same textures so that we don't have to switch them. And we didn't do like a super serious analysis where you could imagine like solving some constraint problem where you make absolutely sure that the things that happen to be in order on this level are definitely next to each other in the texture, but that would involve, some output from the editor.
Yeah, spreadsheets.
And then it changes when you edit the level and all this stuff, right? So instead, it's just more like generally, like look, and especially back then, because the art wasn't super high resolution, it wasn't that bad to say like, okay.
What res was this rent made for? Then 2K.
So the Xbox 360 was 720p. Maybe it could do 1080, but it was infeasible for most games to even try that.
So 1280 at 720.
Yeah, we were targeting 720p at that time. And so if your source textures are 1024 by 1024, which a lot of them were, and if a lot of the pieces are rendered slightly bigger than 1:1, which especially the background sky stuff was, you could fit a lot of stuff in the level into a relatively small number of textures. And so we just sort of do that. And so the job of this tool that I made, which was called the pieced image maker, because pieced image was like the file format. It's like, look at the Photoshop layers, pack them into these textures, and then make a little output file that tells the editor, here's some name like, Rocky Platform A, and that is n rectangles.
An index.
Yeah, it's n rectangles, and these are the coordinates of them
in the texture.
in the texture,
Right.
but also then in like relative to some origin, right? And so then you can drag that thing around as one object and it's like multiple rectangles. I'm sure other 2D systems probably have something
Yep.
similar. It's just like a thing that you want. I'll say for people who don't know this stuff, the reason you want to do that, imagine you have a very simple shape, like a big L shape or like a corner, right? Well, you want to economize on texture space, and which makes the file size of the game smaller and also allows you to pack more things into one GPU texture. So you don't want to store a bunch of transparent pixels that aren't going to impact anything on the screen. But if you have like this giant L shape and you treat it as a rectangle enclosing the L, which is the dumbest, simplest thing to do, it's, 85% waste in transparent pixels, in file size, and actually also in GPU time, because your GPU will spend time blending these 0 pixels with everything else, right? And so it's a great benefit to not do that. And even more so on older computers, right? So that is all just to say that this format that was this, here's a bunch of rectangles glued together that you could drag around in the editor, was a thing that we developed in response to the art process that David was doing. And before that, the programmer art didn't do that. The programmer art was mostly just rectangle with a bitmap on it, and you could stretch it around, right? And so those are kind of very different things.
Why is it like a 2D platformer because, there are many things you could have done. You could have done something more like a top-down sort of thing, or you could have decided it should have been in 3D, or you could have... So there was something that made you pick that. Was that just, hey, a random first guess, and then it stuck? Or were you like, there's a reason?
There are two reasons, two lines of reasoning that came together. One was, hey, when I first went into games industry, didn't even feel like the industry at the time, but doing this bolt action stuff, we did some really hard, challenging thing, and we only had 2 programmers. Like, imagine anyone in the year 2022 saying, I've got a 2-person programming team. We're going to build our own game engine that doesn't even use the graphics API, and it's going to be drop in, drop out, client server, narrow bandwidth action game, and we're going to make it in like a year or 2 years. It's like nobody these days would even try that, and like we somehow did it without even being in games.
Right. So I get getting 3D out of the mix, but now there are many different types of 2D games. There's top down, there's isometric, there's
let me go back to that for a second, right? Because like I said, I'd had a hard time firstly with bolt action, but we made a game. We made several iterations of it. It shipped to people.
Yes.
It was grueling, but we did it. And we were poor all the time and all that. After that, like I said, I was kind of burned out. I worked on other projects like Gallstaff, and there was probably other 3D stuff before Gallstaff. And like everything I did was trying to be 3D in some way. The air guitar game was trying to parse 3D space, right?
Yes.
Like that's even harder.
Yeah.
I definitely noticed the pattern. And so Happy Cake, for example, as we discussed, was completed.
Also
and
3D.
3D. It was a lot of work. We got it done, but also the delta between that and a game that I would have liked was like still pretty big, right? And so I had a good taste for how hard 3D was. I knew that I could do it, but I also knew that it was going to take a lot of time and energy to do it, both technically, firstly, but also in terms of design. Just getting things to feel good in 3D is harder.
Yeah.
Solving issues like, oh, there's just visibility problems here, or collision doesn't feel good, or whatever it is. Those are all easier just from a design standpoint in 2D than 3D.
I see.
Right? And so what I was saying to myself was, I would have envisioned that I would have done a big, groundbreaking, meaningful game. I was about to say important, but I don't know what important means. And I don't think I would have said it that way. But like, I wanted to really make my contribution to games, and I hadn't made a game that was like that yet.
Okay.
Right. So Happy Cake didn't ship to anybody. The bolt action game was played by a 3 or 4 digit number of people.
Right.
And then didn't continue after that.
Right.
So it's like, when am I going to do this thing? And what do I do to maximize the probability that this time this project succeeds? right? And there were many things. I was like, it's time to get serious and stop
Okay.
playing around on all these little projects. Now, we've talked through a lot of the consulting that I did. We talked through a few of the projects that I did, but like there were a lot of little projects. And when we skimmed over like Game Developer Magazine, right? I
Right.
did that for like 3 or 4 years.
Yeah, yeah.
It's like 20 to 30 little projects.
Yeah, yeah.
That whole thing.
Yeah.
It was nuts.
Yeah.
So I was like, okay, let's stop messing around and make a game that's really good. So firstly, eliminate technical challenge and design challenge by being 2D. On the Xbox 360, it was really slow to load things off the so-called disc because it, as an Xbox Live Arcade, this was a thing that was different for Xbox Live Arcade than the rest of it. They had some like extra compressed package format that was, I think, only originally meant for save games or maybe patches. So it had extra security or something. But then the way Xbox Live Arcade was implemented, all data came from that. But the point being, loading data once you were running was way slower than it was for like a AAA game that you bought from the store. And so my approach on that platform was we simply don't load anything after startup. And so the songs were compressed, OGG format, but I would keep the whole thing resident in memory and then uncompress pages as I play them. And then the absurd thing is graphics were compressed. So on GPUs, even back then, you had a set of texture formats that the GPU is fast at decompressing. That's substantially smaller than the uncompressed bitmap would be, but because it has to be fast for the GPU to use, is also not like seriously compressed, right? So the compression ratio is not great. It might be like 6:1. Whereas JPEG might give you like 20, 30:1.
Depending on how much loss you're willing to
Yes,
tolerate, yeah.
yes. As it happened, like 4:1 or 6:1 was not enough to fit the whole game, but 20:1 was. So the ridiculous thing that I did for the 360,
You brought it in as JPEGs and then
all the bitmaps are in memory as JPEGs. And then when you use them on the GPU, I uncompress them to completely uncompress. Because recompressing them to GPU formats takes time too.
Yeah.
And if you're doing it as you load the level, I don't want to do that. So it actually takes more RAM on the GPU than it should by a lot because I'm trying to fit everything into memory the whole time. So that was fun. Here is a simpler version of the Mimic distraction puzzle. I did think of this form of puzzle when designing the original game, but I felt it would be too easy to solve accidentally, or even when solving deliberately, it just wouldn't feel as strong. The aspect of the final design of having to enter a long passage from both sides necessitates more premeditation, and it just feels better to me. But that final design requires special programming to get the rabbit not to leave its area, because if he did go out from beneath the overhang, you could easily just jump on him and kill him. That is to say, this rabbit does not behave quite like the other ones, and the only reason for that is to implement this puzzle. Some designers would consider this a hack that acts as a mild blemish on the game. Here, to prevent the rabbit from being killed, we make the player climb up into a restricted area from which the rabbit cannot leave and cannot be attacked from above. Thus, no special programming hack is required. This initial cliff on the left is here because the rabbit chases you very slowly when you are far away. So, if you were able to wake him up and then walk to the left side of the level, you could coax him to walk all the way over to the left. Then you could successfully race to the ladder and win without using the parallel universe at all. Because that would break the puzzle, we prevent it. Today, with much more design experience, do I like this version of the puzzle better? Probably, as I'm more of a purist about these weird hacks. But there's still something enticing about the symmetry of you and your shadow entering a tunnel from opposite sides, having the rabbit chase you in opposite directions. I wonder if, by working on this further, I could come up with an even better version of this puzzle that retains that symmetry.
Movement Amplified. Is that another novel title? Or
No, I mean,
it makes sense in this level?
it was where this came from was these two levels. I was originally thinking of them as being kind of parallel to each other, and they
Right.
ended up maybe not so much.
Well,
right?
when you get on the cloud train here, including
Yeah.
this first pair of cloud trains,
Yes.
again, so for me at least, for the style of games that I like, this was another one of these wonderful moments where it's like, oh, so is this a new object? Like, is this a super fast conveyor belt? Because you find those sometimes in games, right?
Oh yeah.
But no, it's the same engine following the same rules. It's just that there's a little bit of a recursion here where, well, you're standing on some moving clouds. As time changes, the clouds move, but that makes time change more. And it's also kind of confusing at first, right? That it speeds it up going in either direction. But think about it. It makes sense. If you're running the clouds backwards, they move farther to the left, which means faster backwards. And if you move to the right, they're moving faster to the right, which makes time go faster.
Yes.
And I hope I said that right.
There is also a technical note about this and how it was programmed and why that's the right math. Yeah.
Right. When you realize that this is following from the same physics and the same engine, again, using the word physics somewhat broadly.
Sure.
For me, there's a real pleasure in that because, if every new puzzle has a new widget with new behavior, well, maybe that's not the right way to make more variety. Maybe it's nice to have the variety emerge from the rules. So I really enjoyed both these cloud trains and the next one. And of course, this was a little bit tricky, and I thought at first I had to do something else. It's a nice fact that the key rolls back toward you if you screw up.
Yeah. So here I brought back the left-right gate, right? But
is there any way to?
no,
Yeah, we can't ever use
it's
the
just
right gate.
it's more like a callback to the earlier part of
Right.
the game, right? In case you'd forgotten about it, about your poor performance in that episode, we bring it back.
And so then we have another one of these things again, amplified by time. We have this nice moment. We have to jump on it, even though it's off camera, but it's okay. We know it's going to be there in time to catch us, and there it is. And we can just barely make it onto the next platform.
Which, I mean, really, that's the kind of leap of faith in the game,
Right.
honestly, right?
Right.
Yeah.
So that's nice.
Braid's visuals are very, very dependent on particles. We use lots and lots of particles to create interesting looking motion in both the foreground and background. But all these particles need to rewind perfectly. That was one of the basic principles I adopted early on. The naive way to rewind particles would be just to store in the rewind buffer the position, speed, current color, and so forth of every single particle for every single frame, just like we do for any other gameplay object. And then we just restore those properties when you go backward in time. But this would use a huge amount of memory. Typically, there are only a handful of gameplay objects in a level, but even in the original game, there were thousands or tens of thousands of particles. Storing all that data would eat almost all the memory available for rewind, which would seriously curtail gameplay. Because each frame would take much more memory, we would store many fewer frames, so maybe you'd only be able to rewind for a few seconds instead of the 15 to 45 minutes that you could rewind in the original game. To get around this, particles in Braid work differently than they do in any other game I'm aware of. In pretty much every video game, particles are implemented as follows. You have some function that creates particles each frame, picking random properties like size, color, speed, and so on. Then you have another function that simulates all currently existing particles forward for a short period of time, applying gravity, drag from the air, changing the color of the particle over time, deciding whether the particle has completed its lifespan and should disappear. This function then gets called every frame, and each time it computes the new state of the particle, this just overwrites the old state. Once you've rendered the frame, there's no reason to remember that old state anymore. But under this scheme, particles simply can't go backward because this simulator function isn't bidirectional. Basic rules of physics, like air friction, destroy information. For example, once you've reached terminal velocity, it is not possible to deduce what speed you were going one step in the past. And once a particle has disappeared, you wouldn't know how to recreate it in its final state because all that information is just gone. But the classic particle implementation provides some hints for what we can do to fix this problem. Classically, when the particle is created, we get its random size, color, and so forth from a random number generator, and we were careful to seed that generator with a good value to ensure the output is fairly random looking. When you seed a deterministic random number generator, this determines the sequence of numbers that you will get afterward. That's what deterministic means. In normal situations, you just seed a generator one time. But if we take the unusual step of seeding the generator for each particle, based on some numeric identity of that particle, we could get reproducible results out of that spawner function no matter when and how often we call it. Seeding for each particle puts more demands on the random number generator. Low-quality generators can easily look less random if you seed them too often. And I did have this problem initially. Even higher quality generators can produce artifacted results if you seed with low integers, for example. But there are some simple strategies to just mix the numbers up a little to generate a higher seed value that is still deterministic. In order to make this per particle seeding work, we need an easy way to compute each particle's ID. Since each frame, one thing we do know is what time it is. We build the system so that the time allows us to uniquely identify a particle. For this to work, we take another unusual step, designing the emitters so that each one holds a fixed number of particles only. For example, if an emitter emits 1 particle per second and holds 10 particles, then each particle has a lifespan of 10 seconds. If the current game time is 35 seconds, then the 10 particles in the buffer will be particles number 26, 27, 28, and so on up to 35. These indices correspond to the spawn time of each particle, and thus they uniquely identify each particle. Now if we render a frame at 36 seconds, we will have particle 27, 28, 29, and so on up to 36. And these will all be the same ones as the previous list, except we dropped 26 off the front and added 36 to the back. This strange setup allows us to pick any number whatsoever for the current time. And then we know what particle numbers exist at that time, which means we know how to seed the generator, which means we know what all the particles look like exactly, even if we decide that this frame should be time equals 1 million seconds, and next frame should be time equals minus 1 billion seconds. So all particles have fixed lifetimes, but if we want to give them the appearance of variable lifetimes, we just fade them out faster or slower and just don't draw particles that have faded out all the way. But these particles do still functionally exist. So far, we've just been discussing the creation of the particles, but after they're created, we need to run that simulation function to evolve them over time. How do we do that? In principle, we could just do the classical particle thing and run small simulation time steps for each particle until we get them to the current time. But because we're recreating the particles each frame and our particle buffer holds particles of a range of ages, and some of them might be very old, we have to watch out because each frame we might be simulating way too many time steps and our game could run very slow. You might start thinking, hey, when you're going forward in time normally, you just save the data from the previous frame and you only need to run one time step. You only need to do this complicated, slow computation when going backward in time. Lots of computer science papers encourage this kind of strategy, but it's a bad way to think for interactive programs if you have any alternative. We want rewinding to be natural as walking. In fact, walking is rewinding in World 4. Either we can maintain a solid frame rate when rewinding, or we can't. If we can, then whatever we're doing for rewinding works for going forward too. If we can't maintain that solid frame rate when rewinding, well, that seriously damages the solid feelingness of the game, and we should work hard to change this. So I didn't want to consider some incremental system that has these kinds of problems. I wanted a flat system that would run at the same frame rate always. You might think about reducing the CPU load from the lazy approach by combining many simulation time steps into one so that you're just simulating one step representing a larger duration of time. Or you might try running many small steps but with a simplified function that's cheaper to run. But these approaches would not result in perfect visual reproduction of the particles, and in World 4 this could even result in large objectionable discontinuities while walking, since you can walk left from a frame that you just simulated a moment ago to a frame where you were 5 minutes ago, and these need to line up seamlessly. In general, video game physics gives you different results when you simulate things for bigger or smaller time steps, and games that are carefully crafted might employ a variety of techniques to deal with this problem. So if your particles are doing normal physics, you can't cut corners, you just have to do a lot of computation. However, the particles in Braid don't affect gameplay in any way, they're just cosmetic. So we really have a lot of freedom about what the particle simulation function is. Rather than simulating exact physics that could cause problems for us, like the aforementioned air resistance, we can do simpler things that can be expressed in closed form. For example, a parameter like this particle slows down by 1 meter per second every second. This seems kind of physicsy, but it's frame rate independent, so you can take arbitrarily big time steps. This specific idea of constant deceleration has disadvantages, since if you let the particle live long enough, it will slow down, stop, and reverse direction, which is probably not what you want. But just don't let it live that long, or reduce the slowdown rate. Closed form means we can express the entire evolution of the particle in one short mathematical function, regardless of the amount of time we're simulating it for, and we always get the exact answer. Combined with the deterministically seeded spawning, this gives us the ability to reproduce the state of any particle at any time without storing any per particle data at all. This is how most of the particles work in Braid. Each particle is recreated from scratch and simulated to the current time every single frame, whether we are going forward or backward. The particles don't really exist at all between frames, as we don't keep their data at all. I said that most particles in Braid are handled in a fully deterministic way, where they're regenerated every frame, and apart from that, mostly don't exist. But when I got to World 6, I needed something else. I wanted particles that helped clearly illustrate the slowdown effect of the ring. But the ring is under your control. You can take and drop it any time. So if it slows down the particles, there's no way to represent those particles' positions across time in closed form, which means we'd need some kind of storage for them. On the other hand, if the ring doesn't slow down the particles, that makes the game weaker. So I wanted to come up with a solution for this. So I bit the bullet and stored the positions for some particles only. For World 6, I introduced a new kind of particle emitter called the Rainmaker, which drops the snowflakes that make the most prominent motion. Yes, the Rainmaker drops snow. It used to be rain, but we often don't rename our entities when the cosmetics of the game change. In the Anniversary Edition, we sometimes use Rainmakers to generate additional animated clouds. Because these clouds have a lot of motion, we want them to be slowed by the ring as well. The Rainmaker has a loop that saves out the positions of these particles in a tightly packed, efficient manner, and it also saves out the position of the ring over time, so that we don't have to save out the particle positions every frame. We just simulate the particles forward for some limited number of ring positions, so that we don't spend too much CPU doing this. After a certain amount of time has passed, we record new Rainmaker information with new positions for every particle. If you're familiar with video encoding, it's like storing iframes, which record a full frame of video, and then p-frames, which are just smaller changes from the previous frame. To reconstruct the current state, you just go to the closest previous iframe and then simulate a small number of p-frames. Besides packing the snowflakes efficiently, we just make sure there aren't too many to begin with. We just want to use them to visualize slowdown, so they're distributed through the space enough that we get a moderate density of them everywhere, but we them for the most compelling visuals. Behind the snowflakes, we still have lots and lots of normal Braid particles whose positions are not recorded, so they can't be slowed down. But the art style of World 6 is tuned so that these particles are subtler than they may be in other worlds, and they move more slowly, so you don't really notice that they're not affected by the ring. The snowflakes tend to be much louder in the player's attention. Sometimes we do add particles that move a bit faster, but these tend to be placed far enough from any potential ring drop points that the lack of slowdown is not too noticeable. By doing all this, we are able to achieve our goal. Note that this was a hybrid of technical solution with purposeful art direction. A lot of the best problem solving in games happens as a fusion of multiple disciplines. It's a good idea to always view your problems in a holistic way in order to help see how to bring the different disciplines to bear.